Hello everyone, welcome to the channel. You can see four functional equations are written on the screen. Many of you can answer what is the f of x here that will satisfy the functional equation. For suppose if I ask you what's the f of x in the first equation, you'll reply f of x is equal to kx, where k is a real constant. Similarly, if I ask you for the second one, you'll reply f of x is of the form x power m, where m is a real constant. If I ask you for the third, you'll reply f of x is of the form ln of kx, where k is again a real constant. And if I ask you for the fourth one, you'll reply f of x is equal to a power kx, where k is a real constant. But many of you cannot answer if I ask you how did these equations get these solutions and how can we guarantee that these are the only solutions and no other solutions exist that will satisfy these equations. I welcome you all to the topic that we are going to discuss today, solving functional equations via first principle of derivative. Now let me solve one of the equations from this list and you can try the rest of them on your own. Now you can see one of the functional equation written on the screen. This functional equation has a special name. It is known as Cauchy's functional equation. So let us try solving it. So if I want to solve it using the first principle of derivative, now let me write it first. Now let me think how to use this functional equation to evaluate this limit. We are given f of x plus y equal to f of x plus f of y, right? Now if I replace y with h, we get, now let me substitute this value of f of x plus h in our first principle equation. F dash of x is equal to, we can see that f of x cancels. Here also it is h since we replaced y with h. Yeah. Now we are left with limit h tends to 0 f of h by h. Now how do we deal with this? Now we make an observation in our original equation. If we substitute both x and y as 0, we get f of 0 is equal to twice f of 0, which implies that f of 0 is equal to 0. Now I can write this limit as f dash of x equal to limit h tends to 0 f of 0 plus h minus f of 0 divided by h. It is same as the before one. Now this is nothing but f dash of 0. F dash of x is equal to f dash of 0. Now f dash of 0 is a constant. Let's say f dash of 0 is k. Now you can write as f dash of x is equal to k. Now if we integrate on both sides, we get f of x is equal to kx plus constant. But we know that f of 0 is 0, which will imply that this constant will also be 0. Our final solution is f of x is equal to kx. This is how the first principle of derivative guarantees that this is the only equation that will satisfy the equation. Now, it doesn't guarantee that it will satisfy the equation. We need to manually plug in and check. If we plug it in our equation, we get k times x plus y is equal to kx plus ky. It absolutely holds true. Therefore, this is our general solution to this Cauchy's functional equation. Now we have solved it using the first principle of derivative since we have given that this function is differentiable and it has a real domain. Now what if the function has some rational number domain? How do you deal with it then? You can't use the first principle of derivative, right? You can try thinking it on your own, how to solve the equation when the domain is from rational number and the range is also rational number. Now let us move on to the next question. Here we are given that let f from R to R be a differentiable function satisfying f of x plus y equal to f of x plus f of y plus an expression in x and y. Now in the before equations we could actually see and guess the solutions, but here we can't. Now, first principle of derivative will help us to find the function without guessing it. Now, let us write the first principle of derivative again. Now, again, if I replace y with h in the equation, I get f of x plus h as. Yeah, now I will substitute this into our equation. Now, if I take this f of x to the LHS, I get f of x plus h minus f of x equal to this expression. I'll substitute it in the limit. F dash of x equal to limit h tends to 0, f of h plus 4x cube h plus 6x square h square plus 4x h cube divided by h. Now let us make an observation again. If I substitute both x and y as 0 in the original equation, we again get f of 0 is equal to twice f of 0, which will imply that f of 0 is equal to 0. Now let me write this equation in the next slide. I have just written the equation that we have written in the previous slide. What I have done is slight change. I subtracted an f of 0. Since the value of f of 0 is equal to 0, I don't need to add plus f of 0. I can leave it in this form. Now let's evaluate this limit. I'll break up the h with respect to these terms. Yes, now we can write f dash of x is equal to limit h tends to 0. Now we can substitute h equal to 0. F dash of x is equal to, here from the first principle of derivative, this is f dash of 0 plus 4x cube, and when we substitute h equal to 0 in this one, we'll get 0. Now again, f dash of 0 is a constant, let's call it k. If I integrate on both sides, I get f of x is equal to kx plus x power 4 plus a constant. Now since f of 0 is 0, I will get this constant as 0. Our final answer is f of x is equal to kx plus x power 4. Hope everyone understood. Now let us move on to the third question. It says find all differentiable functions f from minus 1 comma 1 to r where minus 1 and 1 are both not included in the domain, satisfying f of x plus y by 1 minus xy is equal to f of x plus f of y. Many of us from observation can conclude that f of x will be of the form k times tan inverse x. But today we'll be deriving it using the first principle of derivative. But to derive, we need something like of the form f of x plus h. We can't find anything like that in our given equation. So let us try to create it. Let us equate x plus y by 1 minus xy is equal to x plus h. And let us find y in terms of x and h so that we can substitute it in our original equation to get f of x plus h is equal to f of x plus f of y. Let's do it. X plus y is equal to x plus h into 1 minus xy. Now let us simplify this. We can notice that an x is getting cancelled. Now let us bring all the y terms together. We get y into 1 plus x square plus xh is equal to h. Y is equal to h by 1 plus x square plus hx. Now this is what we will substitute as our y in the original functional equation to get f of x plus h term. We will get it as f of x plus h minus f of x is equal to f of, I will not write this expression and simply write it as y. Okay, now we can confidently apply our first principle of derivative. F dash of x is equal to, now let's substitute our previous expression. It will become limit h tends to 0 f of y divided by h. Now let us substitute the value of y. We get f dash of x is equal to limit h tends to 0 f of. Now from our original equation you can also notice that when I substitute both x and y as 0, I again get f of 0 is equal to twice f of 0, which will imply that f of 0 is nothing but 0 itself. So that's why I can write minus f of 0, it doesn't make a difference. Now in order to make this look like our first principle of derivative, I will multiply and divide with 1 plus x square plus hx. Now I can do one thing. This expression is nothing but f dash of 0. And when I substitute h as 0, we will get 1 plus x square in the denominator. Let us substitute f dash of 0 as a constant, which is, let's say, k. F dash of x is equal to k by 1 plus x square. If I integrate on both sides, we can see that we get f of x is equal to k times tan inverse x plus a constant. If I substitute x equal to 0, since we know that f of 0 is 0, this constant will go to 0. And our final solution is f of x is equal to k times tan inverse of x. This is our final answer. We can also notice that we were given minus 1 to 1 in the domain. It is because it will ensure that the product of xy is always less than 1, which will keep our identity tan inverse of x plus y by 1 minus xy equal to tan inverse x plus tan inverse y preserved. If xy was greater than 1, then we had to add a pi on the left hand side to make it equal. Now let us move on to our fourth question. Let f from R to R be a differentiable function satisfying this functional equation for all x comma y belonging to real numbers. We are also given that f of 1 is equal to e. We need to find f of x. Now before we again do the first principle of derivative, you can actually make an observation. If you substitute x as 1 and leave y as it is, you will get that f of y is equal to e power y into e power y minus y square, which is nothing but e power 2y minus y square. But before we think that this is our final solution, let us do a sanity check by substituting this into our original equation. If we substitute it in our original equation, we get e power 2xy minus x square y square is equal to e power 2xy minus x square y into e power xy minus xy square. Now if we simplify this equation, we get 2xy minus x square y square is equal to 3xy minus x square y minus xy square. Yeah, even if we simplify and then get another expression, this will imply that the functional equation the solution for which we got will only satisfy only for specific values of x and y. But our solution is supposed to satisfy for every value of x and y. So this is not our solution. Let us see what we'll get from the first principle of derivative. Let me write up the given equation. F of xy is equal to f of x power y into e power xy minus xy square. Again, in order to apply our first principle of derivative, we need to have an x plus h term, but we don't have it here. But unlike the previous problem, we don't have to do all the algebra to find the value of y that we can substitute to get x plus h. Instead, we can do a simple manipulation. From the first principle of derivative, I can do one thing here. I can take out the x common in the first term, x into 1 plus h by x minus f of x divided by h. Now, if we substitute our y as 1 plus h by x, we will be good. F dash of x is equal to limit h tends to 0. Now let me substitute this from our functional equation. We get f of x power 1 plus h by x into e power x into 1 plus h by x minus x into 1 plus h by x whole square minus f of x whole divided by h. Now let us simplify the limit. F dash of x is equal to limit h tends to 0. I can take an f of x common from this both and I will send it to the left hand side. We will be left with f of x power h by x into, if I substitute this part, if I simplify this part, I can take an x into 1 plus h by x common, x times 1 plus h by x. I'll be left with 1 minus 1 plus h by x, which is nothing but minus h by x minus 1 divided by h. I can cancel the x here. Now let me write this part in the next slide. Let us continue. Now here, in order to simplify this limit further, I'll be using the standard resulting limit, which says limit x tends to 0, e power x minus 1 by x is equal to 1, which implies that if x is tending to 0, e power x can be approximated as 1 plus x. Now here, if we observe this numerator, it is 1 plus h by x into minus h. If h will tend to 0, this part will also tend to 0. So I can approximate 1 plus h by x into minus h as 1 plus h by x into minus h. Now let us start evaluating our limit again. F dash of x by f of x is equal to limit h tends to 0, f of x power h by x into 1 plus h by x times minus h minus 1 whole divided by h. F dash of x by f of x is equal to limit h tends to 0, f of x power h by x minus 1 plus f of x power h by x into 1 plus h by x into minus h divided by h divided by h. You can see that the h will be getting cancelled here, and we know that the solution to this limit will come from limit x tend to 0, a power x minus 1 by x is nothing but a power x, sorry, it is nothing but ln of a. You can use this result. Since a is since here f of x will not vary even if h is tending to 0, we can treat it as a constant and we can write it as ln of f of x. F dash of x by f of x is equal to ln of f of x divided by x. Since here we have h by x, I need to multiply and divide with an x. Now this thing will give us the ln mod of f of x, and this x is left, which will come here in the denominator. And if we substitute h equal to 0 in the next expression, we will get that it is nothing but 1 minus 1. Yes, now we need to solve this differential equation to get to our final answer. Now let me do one thing. I'll take this term to the LHS. F dash of x by f of x minus ln of mod of f of x divided by x equal to minus 1. Now I will divide by the x on both sides, 1 by x on both sides. 1 by x, this will become x square, this will become 1 by x. Now we can notice that our LHS is of the form product rule. This can be written as d by dx of ln mod f of x into 1 by x, which is equal to minus 1 by x. Now I can write it as ln mod f of x into 1 by x is equal to integral of minus 1 by x, which is minus ln of kx, where k is our constant of integration. Now let us raise everything to the power e. We will get f of x power 1 by x is equal to 1 by kx. Now we know that f of 1 is equal to e from the given conditions. If I substitute a 1 in place of x, I get e is equal to 1 by k. This implies k is equal to 1 by e. Now let me substitute it in the equation. Now if we simplify, we get f of x is equal to e by x whole power x. Now before we conclude that this is our final answer, let us verify again from the original functional equation. This was our original functional equation. Now let us substitute the solution that we got. If we substitute, we see that e by xy whole power xy is equal to e by x whole power xy into e power xy minus xy square. Now if we simplify, we can see that 1 by y to the power xy is equal to e power xy minus xy square. Obviously this thing is not always true. It will hold true only for some certain values of x and y. So even this will not be a solution. But wait, did we commit any mistake in our calculation part? No. This is the absolute answer that we will get from the first principle of derivative. Then why is it not working? The reason is that in order for us to get this solution, we substituted y is equal to 1 plus h by x. From the first principle of derivative, we tended h to 0, which implies we tended y to 1. And the differential equation that we got before is a result when y is tending to 1. So the first principle of derivatives is if a function is satisfying this particular functional equation, when y will be tending to 1, it must satisfy the particular expression. And solving that expression, the calculus told us that if there exists a function that will satisfy this, it must be of this form. And when we substituted this function is not satisfying the original functional equation. So we can declare that this functional equation has no solution. Even in the start, when we substituted x equal to 1 and we got f of y equal to some exponential part, it didn't satisfy. But we couldn't conclude that there was no other solution existing. But this guarantees us that there exists no solution. Even if you look back at our previous questions, even in this question, when we substituted y is equal to this form and tended h to 0, we were tending y to 0. And then we were evaluating, the first principle of derivative told us how f dash of x is varying when we were tending y to 0, and the calculus gave us the solution that f of x must be of the form k times tan inverse x if it has to satisfy this solution. And if we do the sanity check, we got the answer. So it was the only solution that could satisfy. Even in this problem, the same thing happened. when we tended h to 0, we were looking at how the derivative was working at when we were tending y to 0. And the calculus gave us the solution, we substituted it, and it worked. So even if we get an answer from the first principle of derivative, we can't guarantee that it's the solution that will satisfy. But it will guarantee that if this solution doesn't satisfy the equation, no other solution will satisfy. You can try this problem on your own using the first principle of derivative so that you can check your learning, and you can also solve the remaining standard functional equations that I have shown in the beginning of the class. Thank you. Take care. Goodbye.